Throughout industrial history, the pursuit of engineering dominance has often pushed companies to their financial limits. Some machines were built to redefine entire industries, while others were designed to showcase national power or technological superiority. In doing so, they demanded unprecedented investment, complexity, and risk. While many succeeded as feats of engineering, they ultimately failed as sustainable businesses, leaving their creators burdened by debt, restructuring, or on the verge of collapse. These 13 heavy machines, whose ambition far exceeded their economic return. From aircraft that reshaped aviation to industrial giants that consumed entire corporate budgets, these projects reveal a recurring pattern. When scale, prestige, or political pressure overrides market reality, even the most brilliant engineering can become financially dangerous. These machines did not merely test technology, they tested the survival of the companies behind them. Airbus A380, the super jumbo that almost sank Airbus. When Airbus launched the A380 program in 2000, it was conceived as a bold statement of dominance over Boeing. The goal was clear: build the largest passenger aircraft in history and capture the high-capacity, long-haul market that Airbus believed would define the future of air travel. What followed was one of the most ambitious and financially dangerous engineering projects ever undertaken by a commercial aircraft manufacturer. The A380 was designed to carry more than 500 passengers in standard configuration and over 800 in high-density layouts. Its double-deck fuselage ran the full length of the aircraft, supported by 4 massive engines and a wingspan exceeding that of any commercial jet before or since. Technologically, it was extraordinary. It featured advanced fly-by-wire systems, extensive use of composite materials, and unprecedented passenger comfort potential. However, ambition quickly collided with reality. The complexity of manufacturing such a large aircraft exposed deep organizational problems within Airbus. Different production sites across Europe used incompatible design software versions, leading to wiring harnesses that did not fit during final assembly. Fixing these errors required extensive redesigns, massive rework, and years of delays. Those delays proved catastrophic financially. Development costs ballooned from an estimated 12 billion euros to well over 25 billion euros. Each postponed delivery triggered penalty payments to airlines and eroded customer confidence. Airbus was forced to issue profit warnings, restructure management, and lay off thousands of workers. At its lowest point, analysts openly questioned whether Airbus could survive the program. Market conditions also shifted against the A380. Airbus had bet on a future dominated by hub-to-hub travel using very large aircraft. Instead, airlines increasingly favored point-to-point routes served by smaller, more fuel-efficient jets, like the Boeing 787 and Airbus's own A350. Filling an A380 consistently proved difficult outside a few major hubs. Operating costs compounded the problem. The aircraft required specially modified airports, reinforced runways, and custom boarding bridges. Maintenance was expensive, and 4 engines meant higher fuel and servicing costs compared to twin-engine long-haul jets. Many airlines found the prestige of the A380 did not outweigh its economic burden. Despite these challenges, the A380 was not a technical failure. Passengers loved it, and it performed reliably in service. But commercially, it never came close to recovering its investment. Airbus delivered just over 250 aircraft, far below what was needed to break even. In 2019, Airbus announced the end of A380 production. The decision closed a chapter defined by extraordinary engineering and near financial disaster. The A380 remains a symbol of what happens when technical success and market reality diverge. Proof that even the greatest machines can push their creators dangerously close to collapse. Concorde, supersonic ambition at an unpayable cost. Concorde was one of the most extraordinary aircraft ever built, but it was also one of the most financially destructive. Conceived in the early 1960s as a joint project between Britain and France, Concorde was designed to make supersonic passenger travel routine. It succeeded technologically, yet nearly bankrupted the governments and companies that brought it to life. From the beginning, Concorde was driven more by political ambition than commercial logic. Britain and France viewed the project as a symbol of technological independence and national prestige. Canceling it would have been a diplomatic embarrassment, so costs were absorbed regardless of economic warning signs. Unlike conventional aircraft programs, profitability was never the primary decision-making factor. Engineering Concorde pushed aerospace limits. The aircraft cruised at more than twice the speed of sound, requiring exotic materials to withstand extreme heat generated by air friction. Its delta wing, droop nose, and Olympus turbojet engines were marvels of design. However, these innovations came with immense development costs and maintenance complexity. Every flight cycle stressed the airframe, increasing inspection and upkeep expenses. Financial problems escalated rapidly. Development costs more than doubled original estimates, reaching levels no realistic sales volume could recover. Airlines showed little interest in purchasing Concorde because operating costs were extraordinarily high. Fuel consumption was immense, seating capacity was limited, and sonic booms restricted overland supersonic flight, eliminating many profitable routes. Ultimately, only British Airways and Air France operated Concorde, and even then under special financial arrangements. Governments absorbed development losses, airport fees were reduced, and fuel costs were mitigated through political support. Without state backing, the aircraft would have been impossible to operate profitably. Western manufacturers closely studied Concorde and reached a sobering conclusion. Supersonic passenger flight was technologically feasible, but economically disastrous. The aircraft could not scale, could not adapt to market changes, and could not survive without subsidies. It delivered speed, but at a cost airlines could never justify. The 2000 crash near Paris, rising maintenance expenses, and post-9/11 traffic declines sealed Concorde's fate. In 2003, the fleet was permanently retired. By then, the program had cost billions and returned almost nothing financially. Concorde remains an icon of aviation history, admired for its elegance and audacity. Yet it also stands as a cautionary tale. It proved that engineering brilliance alone cannot overcome market reality. Concorde flew faster than any airliner before or since, but its ambition demanded a price so high that no company or industry could ever truly afford it. Caterpillar LARC, the amphibious giant, nobody needed. The Caterpillar LARC was conceived during the Cold War as an answer to a very specific military problem: how to move massive amounts of cargo directly from ship to shore without relying on ports. On paper, it seemed logical. In reality, it became one of the most expensive miscalculations in heavy equipment history, pushing Caterpillar into a program that delivered technical success but near financial disaster. Developed in the late 1950s for the U.S. military, the LARC-LX, short for Lighter Amphibious Resupply Cargo, was the largest amphibious vehicle ever built. It weighed more than 100 tons empty and could carry payloads exceeding 60 tons. Powered by 4 diesel engines driving enormous rubber tires, the LARC-LX could travel both on land and in open water, rolling directly off transport ships and onto beaches. Engineering the vehicle was extraordinarily complex. It had to function as a ship and a truck simultaneously, surviving saltwater corrosion, wave impacts, soft sand, and uneven terrain. Caterpillar overbuilt nearly every component to ensure reliability, which dramatically increased manufacturing costs. Each unit required immense amounts of steel, custom parts, and specialized assembly processes. The financial problem was scale. Only a very small number of LARC-LX vehicles were ever ordered, primarily by the U.S. Army. There was no civilian market capable of absorbing such a specialized machine. Ports preferred cranes. Militaries preferred smaller, more flexible landing craft. The LARC-LX existed in a narrow niche that barely existed at all. Operating costs compounded the damage. The vehicle was slow, fuel-hungry and expensive to maintain. Its sheer size limited where it could be deployed, and transporting it required additional ships and logistics. What was meant to simplify supply chains often added complexity instead. Military planners quietly concluded that the concept did not justify the cost. For Caterpillar, the program was painful. The company invested heavily in tooling, engineering talent, and production capacity for a vehicle that would never be built in meaningful numbers. While Caterpillar survived due to its diversified product lines, the LARC LX became a textbook example of how military contracts could become financial traps rather than guarantees of profit. Technically, the LARC LX worked. It did exactly what it was designed to do. Economically, it failed. The vehicle solved a problem that did not truly exist at the scale envisioned by its designers. Today, surviving LARC LX units sit in museums and storage yards, reminders of Cold War excess. They represent a harsh lesson in heavy engineering. Building the biggest and most capable machine does not matter if nobody actually needs it. Big Musky 4,250, the dragline that ate a company's budget. Big Musky 4,250 was not just the largest walking dragline ever built. It was a financial gamble so enormous that it permanently scarred the company that commissioned it. Constructed in the late 1960s for the Central Ohio Coal Company, Big Musky embodied an era when American industry believed any problem could be solved by building something bigger. What it proved instead was that scale can consume profits as easily as it moves earth. The machine was designed for strip mining coal in Ohio. At the time, removing vast quantities of overburden efficiently was seen as the key to profitability. Big Musky stood over 22 stories tall, weighed approximately 13,500 tons, and carried a bucket capable of scooping more than 325 tons of material in a single pass. Just transporting its components to the site required months of logistical planning and specialized infrastructure. Engineering the dragline was extraordinarily expensive. Big Musky was powered by massive electric motors drawing power directly from the grid. It did not use tracks or wheels, but walked on gigantic hydraulic shoes, inching forward at less than half a mile per hour. Every component, from cables to gears, was custom-built, making replacement parts slow and costly. Operational costs quickly became overwhelming. The machine consumed enormous amounts of electricity, and maintaining it required a dedicated crew of specialists. Downtime was expensive, yet unavoidable. When Big Musky stopped, coal production slowed across entire sections of the mine. The company became financially dependent on a single machine that could not be easily replaced or repaired. Worse, market conditions changed. Environmental regulations tightened in the 1970s, reducing strip mining activity. Coal prices fluctuated, and demand became less predictable. Big Musky had been designed for continuous, long-term operation at full capacity. When production slowed, its immense fixed costs remained. By the time Big Musky was retired in 1991, it had moved more than 465 million cubic yards of earth. Technically, it was a success. Financially, it was devastating. The Central Ohio Coal Company and its parent organizations absorbed enormous costs that were never fully recovered. Smaller, more flexible machines ultimately proved more economical. Dismantling Big Musky was itself a massive undertaking. Much of the steel was scrapped, while its iconic bucket was preserved as a monument. Today, it stands as a reminder of industrial overreach. Big Musky did exactly what engineers promised. It moved mountains. What they failed to calculate was the cost of keeping such a giant alive. In the end, the dragline consumed budgets as relentlessly as it consumed Earth, proving that size alone is never a guarantee of sustainability. Boeing 747-8, the final gamble of the jumbo jet era. When Boeing launched the 747-8 program in the mid-2000s, it was a calculated attempt to extend the life of one of aviation's most iconic aircraft. The original 747 had revolutionized global air travel, and Boeing believed there was still a market for a modernized jumbo jet. the 747-8 would become the largest aircraft Boeing had ever built and one of its riskiest financial bets. The aircraft was developed in two variants, the 747-8 Intercontinental Passenger Jet and the 747-8F Freighter. Boeing invested billions to redesign the classic airframe with new wings, advanced aerodynamics, updated avionics, and more efficient GEnx engines derived from the 787 program. On paper, the aircraft promised lower operating costs than earlier 747 models while retaining unmatched payload capacity. The problem was timing. By the time the 747-8 entered service, the airline industry had fundamentally changed. Airlines were abandoning hub-and-spoke networks in favor of point-to-point routes flown by smaller, twin-engine, wide-body aircraft. Jets like the Boeing 787 and Airbus A380 offered lower fuel burn, greater flexibility, and far less financial risk. The very market the 747-8 was designed for was disappearing. Development challenges compounded the problem. Weight growth, engine performance issues, and certification delays pushed back deliveries and increased costs. Boeing was forced to absorb penalties and rework expenses while sales momentum stalled. Orders for the passenger version collapsed, with only a handful of airlines committing to the aircraft. Many customers canceled outright. The freighter variant performed better, benefiting from cargo operators that valued payload volume over passenger economics. Even freighter sales were not enough to justify the program's massive development costs. Production rates were repeatedly cut, and Boeing took significant accounting charges as the financial reality became unavoidable. Internally, the 747-8 strained Boeing's resources at a time when the company was already managing the troubled 787 Dreamliner program. Analysts questioned whether continuing the 747 line made financial sense at all. The aircraft became less a profit generator and more a symbolic obligation to keep the iconic name alive. In 2020, Boeing announced the end of 747 production. The decision marked the conclusion of the jumbo jet era, an era defined by scale rather than efficiency. While the 747-8 was technologically impressive and performed well in service, it never came close to meeting sales expectations. The 747-8 stands as Boeing's final gamble on a fading vision of air travel. It proved that even legendary designs cannot survive when market economics shift. In trying to preserve the past, Boeing built a machine that arrived too late and cost far more than it ever returned. Komatsu D575A, the bulldozer. Too big for the world. The Komatsu D575A holds a unique place in industrial history as the largest operational bulldozer ever built. Introduced in the late 1980s, it was conceived to dominate the most demanding, earth-moving tasks on the planet, particularly in large-scale surface mining. Technically impressive and visually overwhelming, the D575A also became a cautionary tale of how extreme scale can outpace economic reality. Komatsu developed the D575A to meet the needs of massive open-pit mining operations, especially coal mines in North America. Conventional bulldozers required multiple units and repeated passes to move overburden efficiently. Komatsu's solution was radical. Build a single machine so powerful it could replace several smaller dozers. The result was a steel giant weighing over 150 tons and powered by a 1,150 horsepower diesel engine. The machine's size was staggering. Its blade alone could move more than 70 cubic meters of material in one pass, dwarfing anything built before or since. Tracks wider than most pickup trucks distributed its weight, allowing it to push immense loads without sinking. On paper, the D575A promised dramatic productivity gains and lower labor costs per ton moved. In practice, those gains came at an extraordinary price. Manufacturing the D575A required specialized facilities, custom components, and low production volumes. Each unit cost millions of dollars, and only a handful were ever built. Transporting the bulldozer was itself a major operation. requiring disassembly and heavy-lift logistics just to move it to a work site. Operating costs further undermined its viability. The D575A consumed vast amounts of fuel and required highly trained operators and maintenance crews. Downtime was especially costly. When the machine stopped, a significant portion of a mine's earth-moving capacity stopped with it. Smaller dozers offered redundancy. The D575A did not. Market conditions shifted quickly. Environmental regulations, fluctuating commodity prices, and changes in mining practices reduced demand for ultra-large surface equipment. Mining companies increasingly favored fleets of smaller, more flexible machines that could be redeployed easily and maintained with readily available parts. The D575A's specialization became a liability. For Komatsu, the bulldozer was a prestige project that delivered limited financial return. While it demonstrated the company's engineering capability, sales volumes were far too low to justify the investment. The machine never reached mass adoption, and production quietly ended. Today, surviving D575A units are rare, with most retired or preserved as industrial curiosities. The bulldozer did exactly what it was designed to do. What it could not do was fit into a world that valued flexibility over dominance. The Komatsu D575A remains a monument to ambition, proof that being the biggest is not always the same as being sustainable. General Electric U50, the locomotive that broke the builder. The General Electric U50 was born from ambition and competitive pressure, and it nearly collapsed its builder in the process. Introduced in the early 1960s, the U50 was GE's attempt to challenge Electromotive Division's dominance in heavy freight locomotives. To do it, GE pursued size and power at a scale that pushed both engineering limits and financial stability. At the time, U.S. railroads wanted more horsepower to haul longer, heavier freight trains across vast distances. GE responded by effectively combining two locomotives into one. The U50 was built on a twin-engine configuration, using two diesel engines mounted on a single massive frame, supported by 8 axles. In theory, this design delivered over 5,000 horsepower, rivaling multiple locomotives working together. Technically, the concept was sound. Economically and mechanically, it proved disastrous. The U50 was enormous, weighing more than 500 tons and stretching over 90 feet long. Its size created immediate problems. Maintenance was complex, access to components was poor, and failures in one engine often sidelined the entire locomotive. Railroads quickly realized that two separate units offered far greater flexibility and reliability. Production costs were high from the beginning. The U50 used custom frames, non-standard components, and complex electrical systems. GE invested heavily in tooling and engineering to support a locomotive that would only ever be produced in small numbers. Each unit sold carried thin margins, and warranty claims soon erased any remaining profit. Operational reliability sealed the locomotive's fate. The U50 suffered from cooling problems, traction motor failures, and structural stress caused by its immense weight. Railroads reported frequent breakdowns and long repair times. For customers, the promised efficiency gains never materialized. For GE, the reputational damage was severe. The financial impact extended beyond the locomotive itself. GE had aggressively expanded its rail division to compete with EMD, and the U50's failure forced internal restructuring. Resources poured into fixing the design instead of developing more practical models. Analysts later identified the U50 era as one of the most financially dangerous periods in GE's locomotive business. By the early 1970s, most U50 units were retired far earlier than expected. Railroads returned to using multiple smaller locomotives, which offered redundancy and easier maintenance. GE quietly ended production and shifted strategy toward more modular, scalable designs. The U50 remains a powerful lesson in industrial overreach. It demonstrated that raw power and size cannot compensate for flexibility, reliability, and economics. For General Electric, the locomotive nearly broke the builder, but it also forced a hard reset that ultimately reshaped the company's future in rail transportation. Spruce Goose, H-4 Hercules, Howard Hughes' financial black hole. The H-4 Hercules, better known as the Spruce Goose, remains one of the most famous and financially ruinous machines ever built. Conceived during World War II by industrialist Howard Hughes, the aircraft was intended to solve a wartime logistics problem. Instead, it became a monument to ambition unchecked by economics, consuming vast resources while delivering almost nothing in return. The original idea emerged in 1942 when German U-boats were sinking Allied cargo ships faster than they could be replaced. Hughes proposed a massive flying boat capable of transporting troops and equipment across the Atlantic, avoiding submarines entirely. Because aluminum was prioritized for combat aircraft, the plane was constructed primarily from laminated birchwood, giving rise to its enduring nickname, though technically incorrect. From the start, the project suffered from delays and escalating costs. Designing the largest aircraft ever attempted pushed engineering limits well beyond existing experience. The H-4 featured a wingspan of over 97 meters, larger than any airplane before or since for decades. 8 massive piston engines were required to lift it, along with unprecedented structural reinforcement. Every component had to be custom designed, driving costs steadily upward. By the time the aircraft was completed, the war had ended. The original military need no longer existed, but Hughes refused to cancel the project. Instead, he continued funding development largely from his own fortune. What began as a government-supported program evolved into a personal obsession. Estimates suggest Hughes spent over $20 million of his own money, an enormous sum for the era. Financial scrutiny intensified when Congress accused Hughes of misusing wartime funds. In response, Hughes staged the aircraft's only flight in 1947. The Spruce Goose lifted off the water, flew for less than a minute at low altitude, and landed safely. Technically, it proved the aircraft could fly. Economically, the demonstration changed nothing. The aircraft never entered production, never carried cargo, and never flew again. Yet Hughes continued to maintain it in climate-controlled hangars for decades, employing crews to keep it flight-ready. The maintenance costs alone were staggering. No airline, military, or commercial operator had any realistic use for such a machine. For Hughes, the H-4 became a financial and psychological sinkhole. While he remained wealthy, the project drained resources that could have been invested elsewhere. For the aerospace industry, it served as a warning about unchecked scale and prestige-driven engineering. Today, the Spruce Goose sits in a museum, preserved as a marvel of ambition. It stands as proof that engineering success does not guarantee economic sense. The aircraft flew, but the cost of proving that single moment turned it into one of the most expensive dead ends in aviation history. Union Pacific Big Boy, the steam giant that bankrupted an era. The Union Pacific Big Boy was the most powerful steam locomotive ever built, and it arrived at the worst possible moment. Introduced in the early 1940s, Big Boy represented the absolute peak of steam locomotive engineering. It was designed to haul enormous freight loads across the steep grades of the Rocky Mountains. Technically, it succeeded. Economically, it symbolized the end of an entire industrial era. Big Boy was created to solve a specific problem. Union Pacific needed a locomotive capable of pulling long, heavy trains over mountain passes without helper engines. The solution was unprecedented scale. The 4884 articulated design featured 2 massive engine units, a boiler of extreme size and nearly 7,000 horsepower. At over 400 tons with tender, Big Boy was a rolling industrial monument. Building and operating such machines was extraordinarily expensive. Big Boy consumed massive quantities of coal and water, required specialized maintenance facilities, and demanded highly skilled crews. Every mile it traveled came with high operating costs. During World War II, those costs were justified by necessity. Freight demand was enormous, and fuel efficiency mattered less than raw hauling power. The problem was timing. Even as Big Boy entered service, diesel-electric locomotives were proving their superiority. Diesels required smaller crews, less maintenance, no water stops, and could operate continuously with far greater efficiency. Railroads quickly realized that while Big Boy was powerful, it was also inflexible and costly. Union Pacific had invested heavily in steam infrastructure to support locomotives like Big Boy, coaling towers, water tanks, roundhouses, and maintenance shops. As dieselization accelerated in the late 1940s and 1950s, much of that infrastructure became obsolete almost overnight. The financial burden of maintaining steam operations while transitioning to diesel nearly crippled railroad budgets across the country. Big Boy locomotives themselves were victims of this shift. Despite being only a few years old, they were retired by the late 1950s. Their service lives were shockingly short for machines of such complexity and cost. Railroads simply could not justify keeping them running when diesels did the same work for less money. Western engineers admired Big Boy's engineering brilliance, but they also recognized its deeper meaning. It represented a design philosophy pushed to perfection just as the world moved on. Steam had reached its limit, and no amount of scale could save it. Big Boy did not bankrupt Union Pacific alone, but it marked the moment when steam railroading became financially unsustainable. The locomotive stands today as a preserved legend, not just of power, but of an era that spent itself into extinction trying to stay relevant. Antonov An-225, the titan that outlived its manufacturer. The Antonov An-225 was never meant to be an economic aircraft. It was conceived as a solution to a single, extraordinary problem, and in doing so it became one of the most financially unbalanced machines ever built. While it earned global fame and admiration, the An-225 also illustrated how extreme engineering ambition can outlive the organization that created it. The aircraft was developed in the 1980s by the Antonov Design Bureau to support the Soviet space program. Its primary mission was to transport the Buran space shuttle and massive inertia rocket components across vast distances. No existing aircraft could handle such loads, so Soviet planners authorized the construction of something unprecedented. The result was the heaviest airplane ever to fly. Engineering the An-225 required enormous investment. It featured 6 powerful turbofan engines, a reinforced wing structure, a 32-wheel landing gear system, and a cargo hold capable of carrying over 250 metric tons. Nearly every component was custom designed. From a technical standpoint, the aircraft was a triumph. From a financial standpoint, it was a liability from the moment the Soviet Union collapsed. When the USSR dissolved in 1991, the original purpose of the An-225 vanished overnight. Funding disappeared, and the partially completed second airframe was abandoned. Maintaining even a single operational An-225 became extremely expensive. Operating costs were massive. Maintenance required specialized facilities, and there was no guaranteed market for such extreme lift capacity. Antonov attempted to keep the aircraft viable by offering it for commercial cargo operations. The An-225 found niche demand transporting oversized industrial equipment, generators, locomotives, and humanitarian supplies. These missions were spectacular, but infrequent. Each flight generated attention, not stability. The aircraft could not fly often enough to justify the long-term financial burden it imposed on its manufacturer. Western aerospace analysts noted the contradiction. The An-225 was irreplaceable, yet unsustainable. No airline would order one, no fleet could exist, and no modern logistics network was designed around a single aircraft of such scale. The plane functioned more like a flying monument than a business asset. As Antonov struggled financially in the post-Soviet era, the An-225 remained both its most valuable symbol and its heaviest burden. The aircraft required continuous investment without offering proportional return. In this sense, it outlived not just its mission, but the economic model that created it. When the An-225 was destroyed in 2022 during the war in Ukraine, the loss resonated worldwide. It marked the end of an era defined by engineering without compromise. The An-225 proved that something could be technically perfect, yet economically impossible. It did not fail in flight. It failed in the balance sheet, surviving long enough to become a legend, but never a sustainable machine. Lockheed L1011 TriStar, the jet that nearly killed Lockheed. The Lockheed L1011 TriStar is remembered as one of the most advanced commercial aircraft of its generation, yet it also stands as one of the most financially destructive projects in aviation history. Introduced in the early 1970s, the TriStar was meant to secure Lockheed's future in the civilian airliner market. Instead, it nearly ended the company's existence as a commercial aircraft manufacturer. From a technical standpoint, the L1011 was exceptional. It featured cutting-edge avionics, including one of the earliest fully automated landing systems capable of Category 3 auto-land operations. Its wide-body cabin was quiet, comfortable, and designed with passenger experience in mind. Airlines praised its smooth handling and advanced safety systems. In flight, the TriStar delivered exactly what Lockheed promised. The financial disaster came from what powered it. Lockheed chose the Rolls-Royce RB211 engine, a technologically ambitious turbofan that promised superior efficiency and performance. Unfortunately, Rolls-Royce underestimated the complexity of the design. Development delays mounted, costs spiraled out of control, and in 1971, Rolls-Royce declared bankruptcy. That single event nearly destroyed Lockheed. Without certified engines, completed L101, airframes sat idle, generating no revenue while costs continued to accumulate. Lockheed had already invested billions into the program and faced contract penalties, canceled orders, and eroding airline confidence. The company was suddenly exposed to losses it could not absorb. To survive, Lockheed required direct intervention from the U.S. government. In 1971, it received a federal loan guarantee worth hundreds of millions of dollars, effectively a bailout. Without it, Lockheed would have collapsed. Even after Rolls-Royce was nationalized and the RB211 program resumed, the damage was done. Market competition compounded the crisis. McDonnell Douglas's DC-10, though less advanced, entered service earlier and captured airline orders while the TriStar was grounded. By the time the L1011 reached full production, the market was saturated. Lockheed could not sell enough aircraft to recover development costs. Production ended in 1984 after just over 250 aircraft were built, far short of profitability. The losses were so severe that Lockheed permanently exited the commercial airliner business, focusing instead on military and aerospace programs where margins were more predictable. Ironically, airlines that operated the L1011 loved it. It was reliable, safe, and technologically ahead of its time, but admiration did not translate into financial survival. The L1011 TriStar proved that superior engineering cannot compensate for catastrophic risk management. It did not fail in the air. It nearly killed its maker on the ground, becoming a lasting lesson in how a single design decision can determine the fate of an entire company. German Maus tank, the super tank that drained Nazi resources. The German Maus tank was the ultimate expression of Nazi Germany's obsession with superweapons and one of the clearest examples of how extreme engineering ambition can become both a strategic and financial liability. Conceived during World War II, the Maus was intended to be an invincible battlefield machine that could dominate any engagement through sheer armor and firepower. Instead, it became a symbol of wasted resources at a moment when Germany could least afford inefficiency. The Maus project began in 1942 under the direct influence of Adolf Hitler, who was deeply fascinated by heavily armored wonder weapons. German engineers were instructed to design a tank so protected that no Allied anti-tank weapon could penetrate it. The result was unprecedented in scale. Weighing roughly 188 tons, the Maus remains the heaviest tank ever constructed. Its frontal armor reached up to 240 millimeters in thickness, and it carried a powerful 128 millimeter main gun alongside a secondary 75 millimeter cannon, giving it firepower beyond anything fielded by its enemies. From a purely technical standpoint, the Maus was remarkable. Its armor could withstand nearly all contemporary anti-tank rounds. However, achieving this level of protection demanded enormous quantities of high-grade steel, precision machining, and highly skilled labor. These were the same resources Germany was rapidly losing due to Allied bombing, territorial losses, and a shrinking industrial base. Mobility proved to be the tank's fatal flaw. The Maus was so heavy that it could not safely cross most bridges, severely limiting where it could operate. Engineers devised an elaborate underwater fording system that allowed it to drive along riverbeds while powered by an external electrical cable connected to another Maus on shore. While innovative on paper, this solution was completely impractical in combat and underscored how disconnected the design had become from real battlefield conditions. The economic cost was staggering. Each Maus prototype consumed industrial capacity that could have produced dozens of proven tanks, such as the Panzer IV or Panther. Those conventional vehicles were urgently needed at the front, while the Maus offered no realistic path to mass production. As Allied air raids intensified, dedicating factories to such an impractical project became increasingly irrational. Only 2 Maus prototypes were completed, and neither saw combat. As Germany collapsed, the program was abandoned, leaving behind damaged hulls and squandered investment. The Red Army later recovered the remains and assembled a single surviving example for display. The Maus did not bankrupt Nazi Germany on its own, but it perfectly symbolized catastrophic resource misallocation. It demonstrated how overwhelming scale, when divorced from strategy and economics, NASA's space shuttle, the reusable system that was never cheap. The NASA Space Shuttle was conceived as a revolutionary solution to the high cost of spaceflight, promising a reusable system that would dramatically reduce launch expenses and make access to orbit routine. Instead, it became one of the most complex and expensive machines ever built, nearly overwhelming NASA's budget for 3 decades while never delivering the affordability it was designed to achieve. The Space Shuttle program emerged in the early 1970s, during a period of shrinking budgets after the Apollo program. NASA needed political support and long-term funding, and reusability became the central justification. The shuttle was marketed as a space truck that could fly frequently, be quickly refurbished, and launch payloads at a fraction of the cost of disposable rockets. On paper, it appeared economically irresistible. In reality, the design compromises required to satisfy multiple stakeholders created a financial trap. The shuttle had to launch large military payloads, land on conventional runways, and be partially reusable. This resulted in an extraordinarily complex system: a reusable orbiter, solid rocket boosters that had to be recovered from the ocean, and an external fuel tank discarded after every launch. Each component introduced cost, risk, and maintenance demands. Refurbishment proved to be the program's greatest weakness. After every mission, the orbiter required months of inspection and repair. Tens of thousands of fragile heat shield tiles had to be individually checked and often replaced. Engines were disassembled and rebuilt rather than reused like airline engines. Instead of rapid turnaround, each flight consumed enormous labor hours and resources. Costs quickly spiraled beyond expectations. While early projections estimated launch costs in the tens of millions of dollars, the real cost per flight eventually exceeded $1 billion when accounting for infrastructure, workforce, and maintenance. The shuttle flew far less frequently than planned, eliminating the economies of scale that were supposed to justify its existence. Safety concerns added further expense. The Challenger disaster in 1986 and the Columbia disaster in 2003 exposed fundamental design vulnerabilities. Each tragedy grounded the fleet for years, triggering redesigns, investigations, and massive cost overruns. NASA was forced to choose between safety upgrades and mission schedules, both of which strained budgets. Despite these failures, the Space Shuttle achieved remarkable technical feats. It built the International Space Station, deployed and repaired the Hubble Space Telescope, and enabled decades of human spaceflight. Technically, it succeeded. Economically, it failed. By the time the program ended in 2011, the Space Shuttle had consumed hundreds of billions of dollars. It never became cheap, never became routine, and never fulfilled its original promise. Instead, it proved that reusability alone does not guarantee affordability. The shuttle stands as a cautionary lesson that complexity, politics, and ambition can turn even the most visionary system into an unsustainable financial burden.